previous Go board project introduced lookup tables, or LUTs, and at the time I told you it was one of the two most fundamental components inside your FPGA. The second most fundamental component is the flip-flop. And together, flip-flops and lookup tables are your FPGA workhorses. They do all the complicated stuff together. There are other components, but these two are the most prominent. So let's get into talking about what a flip-flop is. A flip-flop, which is also sometimes referred to as a register, and it allows the FPGA to keep state. And what I mean by state is that the FPGA knows what happened previously. A lookup table can tell you what's currently happening and decide what your output is based on what your current inputs are, but a flip-flop can tell you what your output is based on what your previous inputs were. So for example, let's say you want to light up LED 1 if you push the correct sequence of buttons on the Go board. So you might have some sort of special safe password that you want to open, and in order to open the safe or light up the LED, you have to push the buttons in the right order. So you have to push switch 2 first, followed by switch 1 second. Without flip-flops, that's not possible to do just using lookup tables alone. The flip-flops allow the FPGA to keep state so that they know that switch 2 was first pushed and then released, and now switch 1 was pushed and released, and it sees that whole sequence of events and then says, okay, now I'm going to go ahead and light up the LED. Another example that's not possible to do without flip-flops is keeping counters inside your FPGA. How can you increment a counter to the next value if you don't know what the previous value was? So that's what flip-flops are for. They're very fundamental, they're very important, and today I'm going to talk about the most important flip-flop, the D flip-flop. In your classes, you might have been taught about different types of flip-flops. Maybe if you've taken a digital logics course, they sometimes talk about T flip-flops, JK flip-flops, but I have never seen in my 10 years of FPGA experience anything other than a D flip-flop. So that's what we're going to be talking about. And here is the picture of a D flip-flop right here. There are 6 pins on a normal D flip-flop. The set pin, which can set the output to a known value. The reset pin, or clear, which will reset the outputs. The data input, D. Clock input, which is this greater than sign symbol here, Q, which is your output, and Q bar, which is the opposite of Q. So now that I told you what all 6 do, I'm going to go ahead and tell you to ignore 3 out of those and just focus on the 3 most important inputs and outputs to a D flip-flop: the D input, the clock input, and the Q output. Your first question might be, well, what is a clock? I'm not talking about an analog clock. I'm not talking about a wristwatch. I'm talking about a digital clock. This is what a digital clock might look like. A digital clock is a square wave which has transitions from 0 to 1 repeating forever. The reason why clocks are so important is because they drive every single flip-flop pin on your design that has that clock input. So if you have one clock in your entire FPGA design, every single flip-flop shares that exact same clock. And the way you can think about a clock is kind of like a set of gears, where the smaller gear won't turn unless the bigger gear is turning, and the entire FPGA is driven by the clock, which is the biggest gear on the design. So as the gear spins one rotation, it moves the FPGA along one time unit, one clock cycle. Your entire FPGA has no concept of time. Time to your FPGA, it doesn't know how long a second is. It doesn't know how long a millisecond is. The only thing that the FPGA knows to keep track of is clock cycles. So, for example, a clock cycle, a clock might be a 50 megahertz clock. Mega means 10 to the 6th. Hertz is cycles. So 10 to the 6th cycles per second, which is 10 million cycles per second in a 10 megahertz clock. The computer that you are using or cell phone that you are using to watch this video might be powered with a processor that runs in the gigahertz range, which is billions of cycles per second. Most FPGAs use clocks somewhere in the range of 1 megahertz, usually on the low end, to 100, 200 megahertz on the high end. Sometimes you can go even faster than that. But as the clock gets faster, it actually becomes harder to write your code to be able to run at those speeds. So the Go board, for example, uses a 25 megahertz clock, which we will get into using that. So the clock is very fundamental component inside your FPGA because it goes to all the flip-flops. So now that you kind of know what a clock is, I'm going to talk about a few examples of how the inputs and outputs behave on a flip-flop. So here's your clock cycle. And this is going on forever throughout your FPGA. We're just looking at one particular slice of time. So on the very first clock cycle that comes along, we're only looking at the rising edges of clocks inside your FPGA. 99.99% of the time, we're going to be looking at rising edges. For whatever reason, history has decided that rising edges are important, so that's what we're going to be using. You could use falling edges, but let's just never do that. So we have a rising edge here where the 1 is located. We have a rising edge here. We have a rising edge here. Now the way flip-flops work is that they look at the input D only on rising edges and they sample it or register it to the output Q, which is why they're called registers. So what I'm trying to get at is that here's the first clock cycle. Here's the first rising edge. The flip-flop will look at the input D and it'll see a 0. And so the output Q will be 0. And it will continue to be 0 until this second rising edge comes along here, in which case the flip-flop kind of peeks its eye open and looks at the input D and samples it or registers it to the output Q. So knowing that, we can draw what Q looks like, which I've done here. So again, first clock cycle comes along, Q gets sampled, it's low, and it stays low. Even though D is changing in the middle of this clock cycle, Q stays low until the next rising edge comes along. Here's the next rising edge. D gets sampled. Q says, aha, D went high, even though it was back here. Now I'm going high, and now it will stay high. On the third clock cycle, it again samples D. D is still high. Q stays high. Okay? Let's look at another example. Same principle applies. D has gone high on the first clock cycle. So Q sees that, and Q will go high. And then this falling edge is ignored. The next rising edge comes along here. The flip-flop will look at the D input, and it will change the value of Q because now D has gone low. So the output looks like this. So Q has now become a pulse that has lasted for exactly one clock cycle. Okay? I created another YouTube video where I went into a lot more detail about flip-flops and clocks and how they work, and I showed examples of like 2 flip-flops back to back, for example. I'm going to put up a link to that if you want to spend more time looking at some more examples of how flip-flops work. If this is brand new to you, I definitely recommend taking a look at some more examples. This is a foreign concept, but as I said, it's very important to how FPGAs work. So spend some time with flip-flops and with some of their waveforms. Check out my previous video about them, and it's going to be important to get to grasp them fully. The more you work with flip-flops, the more they become obvious, but it does take some getting used to. So for this project, the description is as follows. This project should toggle the state of LED 1 only when switch 1 is released. So now we're going to be maintaining the state of the LED when the switch is being pushed, and it's only going to be toggled when it's released. So we're going to have to put a register inside of our FPGA design that controls the state of the switch. So even when there's no buttons being pushed, we're going to need to make sure the LED stays on or make sure the LED stays off. And the way that we're going to be able to do this is we're going to use what's called falling edge detection. So iSwitch1 is the switch input directly from the button. Let's say you push it down so it goes high, and you hold it down for In this case, I only drew 4 clock cycles, which at 25 megahertz is like 100 nanoseconds, which if you can push a switch that quickly, I'm impressed. But let's pretend that this lasted for a couple milliseconds, maybe 20, 30, 100 milliseconds that you held down the switch for. And then you release it. The FPGA code that we're going to be designing is going to need to see this event here, this falling edge on the switch. And the way we're going to do that is going to become obvious when we go into the VHDL and the Verilog code. So let's go ahead and get started. I'm going to be doing the Verilog code first. If you want to skip to the VHDL code, you can do that. Alright, let's get started with the Verilog portion. Module, let's call it clocked logic. You can call it whatever you like. We're going to have inputs. This is the first time we've seen iClock as an input. And again, I said the clock on the Go board is running at 25 megahertz. Now for this particular project, the frequency of the clock is actually not super important, but it will become important in later projects. We also have iSwitch1, which is the button, and one output. There we go. And now we're going to be introducing something that you haven't seen before, which is an always block. Now, always blocks are extremely fundamental to Verilog code, and what they do is they serve as a container to keep track of a certain group of signals. So I'm only going to be using sequential always blocks or clocked always blocks, which means that this always blocks are only triggered when one of the signals in what's called the sensitivity list changes. The sensitivity list is in between the @ sign and the parentheses. So in here, there would be a sensitivity list. Now, I'm only going to put clocks inside of the sensitivity list. So, and specifically, I'm only going to be looking at the positive edge of a clock. This is the way that I prefer to write code. So there are two types of code. There's sequential code, and there's combinational code. Sequential code is any code that is written that is sensitive to a clock, and combinational code means that it is not sensitive to a clock. So combinational code you can think of as belonging to lookup tables, and sequential code implies that there are registers involved. So the always block is a container for sequential code when there is a clock in the sensitivity list. I threw a lot of vocab words at you, but it will become more clear as we do more projects. So always blocks have a begin and an end. So inside the always block is where we're going to be writing the sequential logic, the registered logic, and we're going to be creating our flip-flops. So the very first flip-flop we're going to be creating is a registered version of the input switch. So I'm going to be calling that R_switch1, and this is the assignment operator. It's called a non-blocking assignment operator. Previously, we've only been using the blocking assignment operator, which looks like this. But for registers, we're going to be using the non-blocking assignment operator. And I won't get into blocking versus non-blocking, but if you Google blocking versus non-blocking with NANDland after that, you will see an article that I wrote, so you can look up more information about that. So this statement right here creates a register. So the iSwitch1 is being registered to R_switch1. I personally, when I write my VHDL and Verilog code, if I'm creating a register and I know I'm creating a register, then I'm going to put R_ in front of it, just because it's easier to find when you do searches, and because it just makes my code easier. I make sure that I'm writing code that I know what I'm doing. So that's just the way I like to do it. And I know it's a register because it is in an always block, and it's in specifically a clocked always block. So that creates a registered version of the input switch. Now the reason why that's important is because the way to look for the falling edge on the input switch is you need to look at not only the current value of the switch that you're pushing, but also the previous value. And the only way you can look for the previous value is if you know the previous value. And so what this statement does is it creates a previous value of the switch. So think about that for a second. If R switch 1 contains the previous value of I switch 1, how can we look for a falling edge on the switch? The answer is that we need to look for the moment in time. There is one moment in time where I switch 1, the current value of the switch, is low, but the previous value of the switch, R switch 1, is high. And that is the falling edge. So to do that, we're going to be writing an if statement, which I think is the first time we've seen an if statement in Verilog so far. If statement followed by open parentheses. If I switch 1 equals, you need double equals here, 1 tick B0, meaning the current value is low. Double ampersand is logical and, so that needs to be true and the following needs to be true. R switch 1 double equals 1 tick B1. Close parentheses. Okay? So what this is saying is that if the current value, I switch 1, is low and the previous value is high, then we have seen a falling edge. So if we've seen a falling edge, then we want to toggle the LED output. So this is going to require another register. I'm going to call RLED1. RLED1 gets the inverse of RLED1. Okay? And what this statement is doing is it's saying only assign the value of RLED1 when the falling edge of the switch is detected. And the value that I want you to assign it to is the inverse of its previous value. So this might be a little confusing because it looks like you're assigning the same signal to itself, but what this actually does is it looks at the value of its current value stored in RLED1, it will invert it, and then it will write it back on the clock cycle, on the rising edge of the clock cycle to RLED1. And what this effectively does is it toggles the state of the LED. So this line toggles the LED, but it only occurs when the falling edge of the input switch is detected. So that's what we're doing. Look for a falling edge of the switch, toggle the state of the LED. Okay? And now our output is called OLED1, so we're going to have to assign OLED1 to RLED1. And assign statements just use a single equals sign and module. So I haven't yet defined R switch 1 and RLED1, so I'll do that. And I'll do that with the keyword reg. In Verilog, reg means register, and I only use it to store signals that I assign in a clocked always block. So again, here's my clocked always block. This signal is assigned here, and this signal is assigned here. So I'm gonna define those now. In this case, they're both single bits. You can define multiple bit registers, but for this project, we just need single bits. RLED1. And I'm going to put an initial condition on them as well. Reg R switch 1 equals 1 tick B0. Okay? And that is it for the Verilog portion. Next, I'm going to show what the VHDL looks like. For the VHDL portion, the very first two lines are going to be the same as they've been in the past. Library IEEE, use IEEE, standard logic 1164.all. And now we're going to create our entity. Give it whatever name you like. I'm going to call it clocked logic, for example. And Emacs makes things easy for me, but I'll run through this with you. So the very first input is iClock. We haven't seen that input before, but that is going to be the clock that drives the flip-flops in this particular design. Then there's iSwitch1. which we have seen before. Its direction is in, and its type is standard logic. And then there's OLED1, which is the output that drives the LED. It's an output, and its type is also standard logic. Okay? And that's it for the entity. So end entity clocked logic. Oop, I already have that line right here. Now the architecture, which is the guts of your entity. I'm going to call mine RTL. You can give it whatever name you like, and Emacs has made things easy for me and populated some stuff. So now we're going to be defining the code for this particular project. And the very first thing I'm going to introduce to you is a keyword called process. Process is an extremely important keyword in VHDL. The majority of your FPGA code is going to live inside of a process, and more specifically than that, it's going to be living inside of a clocked process. There are two types of processes. There can be processes that are combinational processes, which mean that there's no clock involved, and there can be sequential processes or clocked processes, which are processes that do have a clock. They're run with a specific clock. I, generally speaking, do not use combinational processes. It's oftentimes a lot of professors will talk about a combinational process first and go through that. I find them, to be honest, confusing, and it's just much easier if I just say to myself, listen, I'm only going to use a clocked process. And you know what, VHDL, you can do all the same things in a combinational process outside of the combinational process. So this is a little bit of a debate that I have with myself, was whether or not I was going to talk about this. But let's just pretend that only sequential processes exist. You can try to write combinational processes if you want, but I just don't like them. So let's write a sequential process. Process is the keyword here, and actually Emacs actually asks you if you want to write a combinational or sequential. So the next thing is open parentheses. Now inside your parentheses is what's called the sensitivity list. The sensitivity list is the list of signals, inputs, that when they change, the process gets executed. So in a sequential process, this list is almost always just going to be your input clock. So this process is sensitive to the input clock. Now, when I say sensitive, it means that if clock changes, for example, if it goes from 0 to 1 or from 1 to 0, this process will be executed. So process iClock is begin. You can optionally give it a name. I'm going to give it a name. I'm going to call it P register, just to keep track. And then I did say previously that the process is sensitive to both rising and falling edges of the clock, but in 99.9% of the time, we're only going to be using the rising edge of the clock. And so you need to tell the synthesis tools, I only give a darn about the rising edge. So let's look at the rising edge. And the way to do that is with if rising edge iClock. Then rising edge is a function that is built in to the language. I believe it's included as soon as you use standard logic 1164.all. So that's what this is called a package file, and when you have these functions, the functions are making calls to that package file. Not particularly important. Basically, all you need to know is if rising edge iClock looks for transitions from 0 to 1 on the clock. If that occurs, then anything inside this if statement will be executed. So the first thing we're going to need to do is we're going to be needing to create a registered version of the input switch. So let's do that. rswitch1 gets iswitch1. This creates a register. Yay, or a D flip-flop. And the reason we need to do this is because in order to look for a falling edge on the switch, on the button that we push with our finger, we need to know two things. We need to know what's the current value of the switch and what is the previous value of the switch. And a falling edge occurs when the current value is low or equal to 0, but the previous value is 1 or high. And so we need to look for that condition. And the only way to look for that condition is to know what the previous value was. So again, that's the purpose of this register or this flip-flop, is to keep track of the previous value of the switch. And now we're going to be looking for the falling edge, and a falling edge occurs when I switch 1 equals 0, and AND is a logical AND, meaning it's checking to make sure that both statements are true. R switch 1 equals 1. So here you go. If the current value is low and the registered version, or the previous value, is high, then we know that this is a falling edge has occurred, which means that your finger has physically released the switch. So if your finger has physically released the switch, we're going to want to toggle the state of the LED. So we need, since I said the word state, we're going to need a D flip-flop to store the state of the LED. Let's call it RLED1. And what we're going to be doing here is the state of the LED is going to be toggled or inverted, and that's done with the keyword not. That creates an inverter. Not LED1. So what this is doing is it almost looks counterintuitive. It looks like you're assigning the same signal to itself immediately. But what's happening here is that it's looking at the previous value of the LED, it's inverting it, and then it's assigning it to the next value of the LED on the rising edge of the clock cycle. So if the current value is 0 and a falling edge comes along on the switch, then the LED will be inverted, it will become a 1, it will light up. If it was illuminated previously, it will shut itself off. Okay? And we also need to do an end process and match the name, so P register. Again, you can call it whatever you want. And the last thing we need to do is assign the output OLED1 to RLED1. We haven't yet told the tools what is our switch 1 and what is our LED1, so we need to do that. And we're going to be creating two signals for them, and the signals exist between the architecture declaration and the begin statement, so let's put them here. Signal, signal name, RLED1, the type is standard logic, and we're going to initialize them to 0. And we need to define our switch 1 as well. And because I am obsessed OCD, I will align these things, and I think that is it. That should do it. Now the reason I put R underscore in front of this signal name is because I know that I'm going to be assigning R LED1 and R switch 1 inside of a clocked process down here, so it's going to be creating a register. And I do this because it's just easier to keep track of my signals when I'm looking to find them. Like if I just search for switch 1, there's a bunch of different usages of switch 1. I want the registered version, so you can search for the R underscore. So it's easier to find it in your code. It's also more obvious what your code's actually doing. So for anytime I'm creating clocked logic, I like to use R underscore to represent the fact that I know it's going to be a register. So that's it. Your VHDL code is done, and every time you let go of that button, the LED will be changing. So now let's go ahead and build the project and take a look at the results. Okay, I've gone ahead and opened up IceCube and added our design file that we just created. And you could just go ahead and run through synthesis right now, but there's one thing we need to do before that. So we need to add a constraint file. We previously added this constraint file down here under place and route, flow, constraint files. This is our PCF or our pin constraint file. And this tells you the physical pins that our signals get mapped to. So for example, iClock is on pin 15, OLED1 is on pin 56. But we haven't yet told the tools what is the frequency of iClock. So we need to do that. And then we're going to be doing that via a synthesis constraint right here. In other flows, sometimes the timing, it's called a timing constraint file, gets added in down in place and route, but in the lattice tool flow, the best way to do it is to add it during synthesis, and the constraints get populated down through place and route. So let's go ahead and do that. Right click on constraint files, click add files, and then I will link to this in the YouTube description, but you're going to be wanting to get the GoBoard clock constraint.sdc file. So let's add that, and let's take a look at that quickly. What this file is doing is it's creating a clock, and we need to specify the period of the clock. So in this case, we're specifying 40 nanosecond period, which is, like I said previously, the period that a 25 megahertz clock needs. So iClock is running at 25 megahertz, and we've told the tools the period of the clock. Okay, so that will tell the tools important information that it needs to know when running through place and route. So let's go ahead, now that we have our design file loaded in, we have our constraint file loaded in, let's just run everything. Okay, the tools are done running through synthesis and place and route. Let's take a look at our synthesis report first of all, which is .srr file. And if we go down to the bottom, let's make sure, look at that. DFF, D flip-flop. We have used 2 D flip-flops. Congratulations, you now have a design that uses both lookup tables and flip-flops. Awesome. And we see, so it calls them D flip-flops here. It also calls them register bits, not including IOs. We've used 2. And it is seen as well that there is a clock. Total load per clock, iClock has something going on. So there we go. We've created some registered logic. Awesome. Now let's go ahead and look at the output of our place and route. So specifically, we're going to be wanting to look at this timing output, clockLogic timing.rpt. And there is a summary section not too far down. Right here. Here it is. Clock frequency summary. So it sees that there is one clock in the design, the name of the clock is iClock, and the target frequency, which is the target that I gave it via the constraint file, was 25 megahertz. And the actual frequency that our FPGA is going to be able to run is 654.05 megahertz. You might have a different number, but that's my number. That's pretty fast, because what this is basically telling us is that if we had a clock that was 654 megahertz, this design would work. If we had a clock that was 700 megahertz, this design would not work. And the reason where this number comes from, it comes from calculations, the physical properties of the flip-flops. Flip-flops are subjected to some parameters such as setup time, hold time, and propagation delay. Those are the big ones. And the purpose of this project is not going to go into what those specifically are, but that it will become obvious to you how that becomes important in an FPGA design in the future. But for now, just know that we have targeted 25 megahertz, and as long as this frequency number here is larger than our target, this will work. The tools stress worst case temperature, worst case FPGA process, and as long as that number is bigger than our target number, we're good. If that number is ever smaller than our target number, then we get what's called timing errors, which, oh boy, that's a big pain to start when you start dealing with timing errors. So luckily this design's simple enough and the clock period is slow enough, we have no timing errors. And I would imagine that for all the work you're going to be doing with the Go board, the 25 megahertz clock is low enough that you should not have issues with timing errors. But it does become a problem for FPGA designers when you start using faster and faster clocks and you start doing more stuff on your FPGA. Something to keep in your back of your head for later in your FPGA development career. So congratulations again, you have a bit stream that has flip-flops and lookup tables being instantiated. So let's go program the Go board and take a look at the results. Okay, the Go board has been programmed, and now when I hit the switch, sometimes the LED is toggling. That time it toggled, that time it did not toggle, that time it did toggle, that time it did. That time it worked. That time it did not work. Now what's happening here is actually a problem called mechanical debouncing. And so we're going to have to write some code to debounce this switch It's a problem that all switches are subject to, and we can fix that problem inside the FPGA. So that's what the next project's going to be doing. But for now, let's just take a step back and see where we're at. We have successfully written a project that uses flip-flops and keeps the state of the LED. When it is on, it stays on. When it is off, it stays off. And that's done with flip-flops. So congratulations, flip-flops are very important. If you're still not very comfortable with them, don't worry. We're going to be doing lots more work with future projects with flip-flops, and the more time you spend with them, the more comfortable they will get. So let's go ahead and talk about debouncing this LED, this switch, to make that LED work better.